Have you ever looked at one of those control rooms and wondered how a single person can run an entire factory from just one screen? Well, it's not magic, but it is a pretty fascinating journey that the data takes. So, in this explainer, we're going to follow one single piece of information, right from a physical sensor all the way to that display, and we're going to uncover the secrets of how these massive machines actually talk to us.
So let's actually start at the end of the line, the Human-Machine Interface, or HMI as it's called. This thing is basically the command center for modern industry. From this one screen, an operator sees everything: temperatures, pressures, fluid levels, all across the plant. They can fire up pumps, open valves, handle alarms, all with just a touch. It's pretty incredible.
But here's the big question, right? How does that screen actually know the water level in a tank that's hundreds of feet away? That is the mystery we're going to solve. We're going to trace one piece of data from the moment it's born in the real world to its final destination, right here on this screen. Okay, so our journey begins where it all starts, out on the factory floor, in the physical world. This is the exact point where our signal is born.
It all kicks off with a sensor. Now, you can think of sensors as the machine's senses. Just like your fingers feel heat, these little devices measure physical things like temperature or pressure. And then they do something truly remarkable. They translate that physical reality into the language of machines, which is, of course, electricity.
What we've got here is called an analog signal. It's a continuous flow of electricity that perfectly mirrors whatever's being measured. A super common industry standard is the 4 to 20 milliamp signal. So if a tank is totally empty, the sensor sends out 4 milliamps. If it's completely full, it sends 20. And everything in between? That's just a smooth, continuous electrical range. Simple as that.
All right, so now our measurement is an electrical current. Its next stop is the brain of the whole operation, the Programmable Logic Controller, or PLC. And inside this digital brain, the first and maybe the most important translation is about to happen.
So, that 4 to 20 milliamp signal travels into the PLC's analog input. Now, inside, there's a crucial little piece of hardware called an analog-to-digital converter, and it gets right to work. It takes that smooth, continuous wave of electricity and basically chops it up into a very specific number. And this right here is a huge deal. Our signal is no longer a physical property. It's not even an electrical current anymore. It has officially been digitized. It's now just a number, a piece of data sitting in the PLC's memory, ready to be processed.
But here's the thing, it's not just any number. When our sensor is maxed out, sending that full 20 milliamps, the PLC doesn't see 100 or full, no. It sees a very specific and, let's be honest, kind of strange number. So let's dig in and find out why.
The magic number is 27,648, a full tank, maximum pressure, 20 milliamps of current. Inside the computer, it all becomes the integer 27,648. But why that? Why not a nice round number like 1,000 or 10,000? Well, it turns out there's a very, very clever reason for it. So, first, a little bit of context. Computers use different sized boxes, you could say, to store numbers. For our signal, the PLC uses what's called a 16-bit integer, or an INT. Just think of it as a box that's the perfect size for holding the kind of numbers we're dealing with here.
Now that 16-bit box can hold any whole number from negative 32,768 all the way up to positive 32,767. This is our entire numerical playground, the full range of values we can work with. And our magic number, 27,648, fits very comfortably inside that range.
And here it is, the big reveal, laid out in an industry-standard mapping table. You can see it right there. 4 milliamps, our minimum, gets mapped to the number 0, and 20 milliamps, our maximum, maps directly to that value, 27,648. It's simply an agreed-upon standard that everyone uses.
But again, why that specific number? Well, by capping the normal operating range at 27,648, the engineers cleverly created a safety buffer at the top of the scale. See, if the PLC ever reads a number higher than that, let's say it sees 30,000, it instantly knows something's wrong. Like maybe a sensor wire is broken. It's a brilliant, built-in safety check.
Okay, so the PLC has its number, 27,648. That's fantastic for the computer, but it's completely meaningless to a human operator. So the final step in this journey is to translate this raw number into something we can actually understand on the screen.
This whole process is called scaling. And really, it's just a translation.
The PLC takes that raw machine language number range, 0 to 27,648, and it converts it into a human-friendly range, like, say, 0 to 100%, or a temperature in degrees.
So how does it do this? Well, inside the PLC's programming, there are these pre-built functions for exactly this job. You've got a function block, often just called scale, that takes the raw number as its input. You just tell it the human-readable high and low numbers you want, and the block just handles all the math for you. It's super convenient.
So, let's see how this plays out. If the scale function gets an input of 0, it spits out 0.0%. If it gets 13,824, which is exactly half of our maximum, it outputs a perfect 50.0%. And if it sees our magic number, 27,648, you guessed it, it outputs a clean 100.0%. The translation is complete.
And this scaled human-friendly number is what actually drives the graphics you see on the HMI screen. A value of 100.0 tells that tank graphic to show itself as 100% full. And then the PLC can use that same value in its own logic, like saying, hey, if the level is greater than this set point, go ahead and turn on that pump.
So far, all the information has only flowed one way, from the machine to the screen. But for real control, you need communication to be a two-way street.
This is where unscaling comes into play. It's the exact reverse process. When an operator types 100% on the HMI screen, a similar function block translates that command back into the machine language number 27,648, which can then be sent out to control a valve or a motor.
And that, right there, closes the control loop. We've gone from a physical property to an electrical signal to a raw digital number to a scaled value on a screen, and then all the way from a human command back to a signal that controls the machine. We're no longer just watching what's happening. We're now part of the conversation. So that's it. The secret journey of industrial data, from a humble sensor all the way to a complex interactive screen. You know, these interfaces are really our windows into the hidden world of machines. And it really makes you wonder, as automation and AI get even more advanced, what are these windows going to show us next?